Good day. By now you must know me. My name is Douglas Harder, and in this topic we're going to give a course summary of what we've seen over the past 36 lectures. So in this topic we will review this course in numerical analysis. We will describe the material that was covered and highlight the interesting aspects involved. So in this course, we began by observing that there were issues with representing real numbers by finite precision floating point numbers. There were benefits to this representation, but there are also drawbacks. We introduced a number of tools that could be used for approximating solutions to numerical problems and that could mitigate some of the issues involved with using finite precision floating point numbers. We then looked at 4 different categories of numerical problems, evaluating the value of an expression to a numeric value, approximating solutions to algebraic equations and systems of algebraic equations, approximating solutions to analytic equations and systems of analytic equations. And finally, we focused on unconstrained optimization, finding maxima and minima. Now, in the course, we started by defining absolute error, relative error, and percent relative error. We looked at the decimal and binary representations of real numbers. We defined rounding a value to a given number of digits or bits, that is, binary digits. We defined the measure of significant digits. We defined accuracy and precision. Accuracy is yielding a result that is close to the correct value. Precision is yielding results with a consistent number of significant digits. Next, we considered the representation of real numbers on the computer. We considered fixed point representations of integers and real numbers. We then considered the benefits of floating point representations, which parallels scientific notation, storing a sign, a first digit or bit, the significans, and of course the mantissa, as well as an exponent. We looked at a 6 decimal digit floating point representation, which was followed by a binary double precision floating point representation, which is used in computers today. We considered arithmetic operations and comparison operations for both of these representations. We looked at the fact that there is a loss of precision when using floating point operations. We have to deal with subtractive cancellation, and we even lose associativity. So x plus y plus z may change in value depending on whether or not you add y and z first or x and y first. Finally, we looked at representations of infinity, not a number, that is, indeterminate values such as 0 over 0, and denormalized numbers. Next, we looked at 7 tools that we would use either to develop or analyze numerical algorithms or describe patterns that would appear repeatedly in our algorithms. We started with averages, weighted averages, and convex combinations. The average is just the sum of n entries divided by n. The weighted average is a linear combination of those objects where the sum of the coefficients equals to 1, and convex combinations when all of those weights are greater than or equal to 0. Now, in this topic, we actually discussed a problem. If we were uniformly sampling random numbers taken from an interval from A to B, where we did not know what A and B are, then we saw that a weighted average of the minimum and maximum values we found gave a better estimate of A and B than any other value. We also saw that different weighted averages of points on a function gave a better estimate of an integral than others. Later, we actually saw that this was the case because the weights that gave us the best approximation, 1/6, 2/3, and 1/6, were actually a consequence of interpolating quadratic polynomials in a technique we saw as Simpson's rule. Next, we proceeded to iteration and the fixed point theorem. We saw an iterative algorithm that appeared to converge to the square root of 2. Later, we saw that this was actually just a special case of Newton's method, specifically Newton's method applied to the algebraic equation x squared minus 2 is equal to 0. So on the left-hand side, we see it in Newton's representation, whereas on the right-hand side is the formula that was known to the ancients. We also described the fixed point theorem. So if we start with an initial value x0 and a function f of x, if we define the iterative procedure where the next value of x is the function evaluated at the previous x value, then if this sequence converges, it must converge to a solution of the equation x equals f of x. Next came linear algebra. Now, you already have seen Gaussian elimination and backward substitution in your course on linear algebra. However, we also introduced the concept of partial pivoting. This was an algorithm that we introduced that allowed us to solve a system of linear equations, and one that mitigated some of the issues that arose from using finite precision floating point numbers. The fact that adding a large number onto a small number essentially wipes that smaller number completely out, or at least loses a significant component of that smaller number's precision. We also looked at an iterative technique to approximate a system of linear equations. This was the Jacobi method. We also saw that some systems of linear equations will result in poor numerical approximations no matter what algorithms we use, simply because the errors in the values or vectors we find are going to be always magnified. So we found that we could describe the ill conditioning based on a value known as the condition number, a value that can be found in programming languages such as MATLAB. And if the condition number is very large, this indicates that there's very little we can do. We are going to get poor answers when we are solving systems of linear equations, and consequently our goal will be to use systems of linear equations that have small condition numbers. Next, we saw interpolation. We started with linear interpolation, then quadratic, and then we described general interpolation with polynomials. We noted that we could find interpolating polynomials by solving a system of linear equations. In fact, finding an interpolating polynomial of degree n which would interpolate n+1 points, would result in a system of n+1 linear equations in n+1 unknowns. We saw that this defined a Vandermonde matrix when we were setting up such a system of linear equations. And we saw that it was easy to set up some points where we tried to find an interpolating polynomial, but where if we did not use partial pivoting, the resulting interpolating polynomial did not actually pass anywhere near the points we were trying to interpolate, hence the need for partial pivoting for Gaussian elimination. We also found that shifting the points towards the origin and scaling resulted in a Vandermonde matrix that had a smaller condition number and consequently resulted in interpolating polynomials that gave us much more desirable results. We also saw that equally spaced points tended to have Vandermonde matrices that had smaller condition numbers. Again, something we have been looking forward to doing to reduce the error of the systems. The fifth tool is Taylor series. Now, we revisited Taylor series from first year and we introduced an alternative notation. Rather than writing it in terms of a point x0 and an unknown value x, we instead wrote the function as f at x plus a small value h in terms of the value of the function and its derivatives evaluated at the point x. We also introduced the idea of using big O notation to represent the error. Consequently, the above nth order Taylor series approximation has an error that is big O of h to the n+1. We also introduced bracketing, and when we introduced bracketing, we described the idea of bracketing a solution to a problem, and we saw how a binary search was essentially bracketing the value we were looking for within an array. However, we then also introduced the concept of an interpolation search, one that converges more quickly. Later, we saw that the bisection method, which was a method for approximating a solution to an algebraic equation, and we saw that that technique parallels the binary search technique. We also saw the bracketed secant method, and this paralleled the interpolation search that we just described when we introduced this topic. Finally, we revisited the intermediate value theorem. So, given a continuous function defined on an interval a to b, and given a value y that falls between f at a and f at b, then there must be a value of x between a and b such that y is equal to f at that point x. Consequently, if we have n x values on the interval a to b, then given a convex combination of this function f evaluated at these n values, then there must be a xi lying between a and b such that f at xi equals that particular convex combination. Following this, we did a deep dive into looking at and categorizing the sources of errors in modeling and numerical algorithms. We indicated that some errors simply are random, errors that result from the inability to make perfectly precise and accurate measurements. We saw that random errors can be described through statistical distributions, which you will see much more of in your courses on statistics. In this course, we quickly introduced you to normally, uniformly, and Poisson distributed errors. However, there are also systematic errors, errors that we can measure and consequently compensate for in our models. Then we looked at some of the sources of errors. Now, of course, some of the error is coming from floating point truncation due to the fact that floating point numbers have finite precision. However, we also described model errors, environmental, drift, production, and calibration errors. We also described how averaging repeatedly sampled readings will actually minimize random errors when we are trying to estimate a particular fixed value. Now, having covered these 7 tools and sources of error, we then looked at 4 categories of numerical problems: approximating the value of expressions, approximating the solutions to algebraic equations and systems of algebraic equations, and here we had linear equations and systems of linear equations, together with nonlinear equations and systems of nonlinear equations. The first were found or approximated using techniques from linear algebra. The nonlinear equations and systems of nonlinear equations were reduced to root-finding problems. Next, we looked at approximating the solutions to analytic equations and systems of analytic equations. This included differential, integral, and integro-differential equations. However, the latter two are also regularly and normally reduced to differential equations, at least by engineers. Finally, we looked at approximating solutions to unconstrained optimization problems. So, our first problem was evaluating an expression to a floating point number. We started by seeing that Horner's rule is the most efficient and accurate algorithm for evaluating a polynomial at a point. The runtime is order n, where n is the degree of the polynomial, and this algorithm required a minimal number of additions and multiplications. Our first class of problems we could also use such interpolating polynomials to evaluate or estimate the value of a function between those points. And we saw that the most appropriate technique to do this was to shift and scale the x values to either the left set if we had 2 x values or the right set if we had 4, and then we could find the interpolating linear polynomial or cubic polynomial and evaluate that at a value of delta between -0.5 and 0.5, which gave us a reasonable estimate of the value of the function between the original points. Now, also we saw that we may be evaluating data that comes from sampled data in real time, and so consequently we may only have historical data, so instead we want to evaluate data in the most recent time interval, and so once again we shift and scale the x values to match the points on the left for 3 points, finding and interpolating quadratic, or 4 points, finding and interpolating cubic, and then evaluating the function on that last interval by evaluating the polynomial we found at some value of delta between, again, negative 0.5 and 0.5. We found that we could approximate the derivative. So in this particular technique, we found an interpolating polynomial and we differentiate it. Then, using Taylor series, we determined that the error was order h squared. If we interpolated 2 other points, then we found that this was the formula, but the error was not as good. It was order h. If we wanted to use only historical data, we could use this formula to approximate the derivative at t. And once again, we found this using an interpolating quadratic, which was then differentiated and evaluated at t, and then we used Taylor series to determine that the error was order h squared. These were centered and backward divided difference formulas. We also saw that we could approximate the second derivative. So finding an interpolating quadratic differentiating twice gave us this approximation, and Taylor series indicated that the error was order h squared. If we use this same formula but shifted, Taylor series indicated that the error dropped from order h squared to order h. So if we wanted an order h squared approximation that used only historical data, we had to use this 4-point approximation. We also found that we can approximate integrals across an interval. So if we just interpolated 2 points, finding the interpolating polynomial, linear, and integrated that, we get this formula. And we argued that Taylor series would show that this is order h cubed. We then saw Simpson's rule. So this gave us a better approximation, one that was order h to the 5th. However, we also saw this approximation, which we found by interpolating 4 points, but then only integrating over the central 2 points. And this also was an order h to the 5th approximation. We could also rely only on previous information. So we could integrate from b minus h up to b by sampling the function at b, b minus h, and b minus 2h, which gave us Simpson's rule, but only integrated on the right-hand side, which had an order h error of h to the 4th. And if we found an interpolating cubic through 4 points, but again only integrated that interpolating cubic from b minus h to b, we got this formula, which was once again order h to the 5. Finally, we saw that we could use these algorithms over and over again, or composite applications of these algorithms. And what this allowed us to do was reduce the size of h and therefore reduce the error. But we saw in every single case, interestingly enough, as a result of the error term, that the error term was reduced by 1. So an order h to the 5th formula was reduced to an order h to the 4 formula. Finally, we considered least squares best fitting polynomials, specifically linear and quadratic, on equally spaced points as a basis of evaluation. So we approximated the value of a function at a point. We estimated the derivative at a point, and we estimated the integral between 2 points. Again, the points are equally spaced, but now we are assuming that there is significantly more noise or error with each of the readings, something that may definitely be the result of data that is being read from a sensor. Now, a reminder, when we were finding least squares best fitting polynomials, we created a Vandermonde matrix, but we only included the columns that corresponded to the terms we were interested in. Consequently, we then solved not v times a equals y, but rather we had to multiply both sides by v transpose. So for linear, this gave us a system of 2 linear equations and 2 unknowns, whereas for cubic systems, this gave us a system of 3 linear equations in 3 unknowns. Now, to evaluate the best fitting polynomial between n plus 1 points, assuming that these have been read and are mostly historic, with only the most recent point being the most recent value, we shifted and scaled the x values so that they lined up to the points -n all the way up to 0, respectively, and then we evaluated the polynomial at some value delta between -1 and 1. Between -1 and 0 was if we were estimating a value that had occurred in the last time interval, and a value of delta between 0 and 1 meant we were extrapolating into the future what a potential value may be one time step into the future. We looked at both linear and quadratic best fitting polynomials for this purpose. We found, however, also that we could update these polynomials in order 1 time, meaning we can find and update. We can find the initial interpolating polynomial in order n time, but once we found that initial one, we can update it in order 1 time with every new reading. We also found that we could approximate the derivative. So if we were approximating around the most recent point, t sub k plus delta times h, where h is the step size, the approximation of the derivative was either that first expression there if we were finding an interpolating linear polynomial or a best fitting linear polynomial, or the second formula if we were finding a best fitting quadratic polynomial. We also found that we could approximate the integral. So we could approximate the integral over the most recent time interval by integrating the best fitting linear or quadratic polynomial, which gave us one of the 2 following formulas. Similarly, we could estimate the integral over the next time interval. So our most recent reading was at time t sub k, and we'd like to estimate the value of integrals 1 time step into the future. Well, in this case, if we were using linear best fitting polynomials, we'd use the formula on the left, or if we were finding a best fitting quadratic polynomial, we would use the formula on the right to estimate the integral over the next time interval. Our second class of problems was approximating solutions to algebraic equations and systems of algebraic equations. We started by seeing that the quadratic formula was not necessarily the best formula to find the roots of a quadratic polynomial. We transformed nonlinear algebraic equations to a root finding problem in one variable. We then saw more advanced techniques for iterative algorithms for approximating solutions to systems of linear equations. And finally, we generalized Newton's method for approximating a solution to a system of nonlinear equations. That is, finding n simultaneous roots for n independent variables. We started with the quadratic formula, and we saw that there were actually two different formulas for calculating the roots of a quadratic polynomial. The formula on the left is what you saw in secondary school. The formula on the right is found by rationalizing the numerator of the formula on the left. The formula on the left is excellent for finding the largest root in absolute value. The formula on the right is best for finding the smallest root in absolute value. Next, after having transformed a nonlinear algebraic equation to a root-finding problem in one variable, we looked at Newton's method, which used Taylor series approximations where we converted the nonlinear equation locally to a linear equation, which we then solved. Next, we saw the bisection method, which used bracketing. This was followed by the bracketed secant method, which uses the same approach as the bisection method, bracketing the root, but estimates the location of the root using a linear interpolating polynomial. We then looked at the secant method. The secant method used the same technique as the bracketed secant method. However, it did not assume that our points bracketed the root. Instead, it was more free to converge towards the root if it was indeed converging. This technique was order h to the phi, which was better than the two previous techniques, which were order h, but not as good as Newton's method, where Taylor series showed us that the error was order h squared. We then saw Euler's method. Euler's method used an interpolating quadratic to estimate the root, and the issue here was we had to set the system up so that we were finding the smallest root. That is, so that we could use the formula -2c over b plus or minus square root of b squared minus 4ac to find the next value in our iteration. As an alternative approach, there was also the inverse quadratic interpolation method for finding the root, where we found a quadratic that interpolated the inverse of the function we were trying to find the root of. Consequently, evaluating that quadratic at 0 gave us also a good estimate as to where the root was. Both of these techniques were order h to the mu, where mu was 1.8 and change. Finally, we saw the Brent-Dekker method. The Brent-Dekker method assumed we had bracketed the root, but then uses bisection, the bracketed secant method, or the inverse quadratic interpolation method to converge on the root. And it tried to always use the inverse quadratic interpolation method, except when it could demonstrate that there was a high likelihood that it would give an inappropriate result, in which case it fell back on the bracketed secant method, which, if that failed, it fell back on the bisection method. We also saw two more advanced techniques for iterative algorithms for approximating systems to linear equations, and these were the Gauss-Seidel method, where, unlike the Jacobi method, we just simply calculate the next vector in one shot, Gauss-Seidel updates the entries as they are found. Not a bad idea. However, we also saw the method of successive over-relaxation. This is a technique where if you know you are headed towards a solution, why not move another 5 or 10% in that direction anyway, under the assumption you are still undershooting the solution. So both of these techniques can significantly speed up the convergence of the Jacobi method, which we saw at the start of the course. We then generalized Newton's method for approximating a solution to a system of nonlinear equations. What we did is we converted the nonlinear root finding problem into a linear root finding problem, which gave us a problem that we can solve with using linear algebra. So consequently, we calculated the Jacobian, multiplied by an unknown delta u sub k, and that had to equal the negation of the function evaluated at that point u sub k. Consequently, the next approximation would be the previous approximation plus this delta u sub k, which we found by solving this previously defined system of linear equations. Interestingly enough, if you were to reduce this to a system of one linear equation and one unknown, you would observe that it does faithfully convert back to the formula we saw for Newton's method. And this technique, its convergence is still order h squared. Our third class of problems was approximating solutions to analytic equations and systems of analytic equations. Specifically, we reduced all analytic equations, including integral and integral differential equations, to simply differential equations. This is the standard engineering approach. We started by approximating solutions to initial value problems, or IVPs. We continued by approximating solutions to boundary value problems, or BVPs. We then proceeded to approximate solutions to problems in partial differential equations, although we focused on 3 very specific problems with partial differential equations. We started by approximating first-order IVPs using solvers that were actually similar to that of composite integration. We started with Euler's method, which was derived directly from the Taylor series formula, which also gave us the error. I then introduced Hoyne's method, and we saw that Hoyne's method, in a sense, parallels the trapezoidal rule, and the error is less than that of Euler's method. Because so many students asked, I even derived the error of Hoyne's method, and it was many, many pages of tedious algebra and calculus. I then introduced, without proof, the fourth-order Runge-Kutta method. Now, the errors of these 3 techniques are order h squared, h cubed, and h to the 5th. But if we were to apply these on multiple steps, then once again, in all cases, the error is reduced by 1. Hence the name fourth-order Runge-Kutta. We also discussed at this time how we could use cubic splines to approximate the solutions between the points that we found in our approximation. So, using these techniques, we'd estimate the value at t0, t naught plus h, t naught plus 2h, and so on and so forth. But what happens if we wanted to approximate the solution at, say, t naught plus 0.3 times h? For this, we could use cubic splines. So, similar to interpolating polynomials, but now we are matching the values at two endpoints and the slopes at those two endpoints. We proceeded then to find adaptive techniques for approximating solutions to first-order initial value problems. Specifically, we introduced this Euler-Hoyne technique, an idea I came up with myself, where we used Hoyne's method to estimate the error of Euler's method. This was used to introduce the concept behind the Dorman-Prince method, where at every single step we are using a weighted average of the value of the functions at various points. In fact, almost always there were convex combinations, but they were weighted averages to estimate the solution to the initial value problem. What these techniques did is that they chose the appropriate step size at each step of the iteration to ensure that we got the desired accuracy we were looking for without having any more function evaluations than necessary, but not having too few function evaluations so that the error was too large. We then proceeded to find solvers for systems of first-order IVPs. But this was easy, because all the previous techniques, Euler's method, Hoyne's method, fourth-order Runge-Kutta, our Euler-Hoyne hybrid, and the Dorman-Prince method, all of these can be trivially extended to solving systems of first-order initial value problems by simply using vectors instead of scalars in the formulas in question. We then proceeded to find solvers for higher order initial value problems. Let's say we had a fourth order differential equation. Well, we saw that we could simply convert an nth order initial value problem into a system of n first order initial value problems. And we already have tools for solving such problems. Finally, we concluded that we could convert any system of higher order initial value problems into a larger system of first order initial value problems. Again, where we already have the tools as we have described above. We then continued to approximating solutions of boundary value problems. We started with the shooting method. We essentially transformed our boundary value problem into a system of two initial value problems, which we then iterated upon in order to converge to a solution to the boundary value problem. We then continued by using our divided difference approximations of the derivative and the second derivative to create a system of linear equations. We then found an approximation to the solution of the boundary value problem by solving this system of linear equations. We called this method a finite difference method, and this is contrasted with a finite element method, which is a more advanced technique for dealing with systems which cannot be easily described using a grid. We also introduced Neumann, and specifically insulated, boundary conditions, and we saw that this would simply lead to small changes to our finite difference approach, where we create and specify various entries of either the matrix or the target vector to deal with insulated or Neumann boundary conditions at either end. Recall that an insulated boundary condition says that the derivative at that end is 0. We concluded by approximating solutions to partial differential equations. We started in one dimension, where we approximated solutions to the heat equation, the equation that describes how heat moves throughout a system. And as we were in one dimension, it would be the same as if we were following heat moving through a wire, or perhaps if an entire surface of a block is being heated simultaneously and that heat transferring through that block. We also looked at the wave equation. So once again, we could describe water waves or electromagnetic waves. We then went on to 2 and 3 dimensions, where we first began by discussing solution to Laplace's equation. Now, we saw that approximating solutions to Laplace's equation was equivalent or similar to that of the finite difference technique for approximating solutions to boundary value problems. We essentially converted the partial differential equation into a finite difference equation, which then gave us the entries of a system of linear equations. We then solved it, and we then had approximations of our solution. We then discussed approximating solutions in 2 and 3 dimensions to the heat equation and the wave equation. So we could actually watch heat and waves propagate across a medium. Our fourth and last class of problems was approximating solutions to optimization problems. Now, we restricted ourselves to unconstrained optimization, that is, finding extrema that are local. You are welcome, of course, to look at various courses that look at constrained optimization, which uses algorithms such as simplex to solve them, often in linear time. Now, we reduced the problem of finding maxima to finding minima. So in all of our topics, we focus on finding local minima to functions. We started by approximating minima to real valued functions of a real variable. We then continued by approximating minima to real valued functions of a vector variable. To find the minima of a real valued function of a real variable, we looked at the following algorithms. We started with step-by-step optimization. This was a very naive technique which just walked forward until it got to by a step size h, until it determined it was in the vicinity of a minimum, in which case it then started to reduce the value of h until it converged sufficiently. You can think of this as almost a bracketing technique. Next, we saw Newton's method for finding extrema. This was essentially applying Newton's method to the derivative. Now, if we know what the function is as an algebraic expression, then what we can actually do is use automatic differentiation for this. However, we also looked at the golden ratio search, which didn't require the derivative. This is a bracketed technique similar to that of the bisection method. However, now we needed not 3 points, but 4 carefully chosen points to reduce the interval on which the minima almost certainly is. We also looked at a concept of successive parabolic interpolation. So, given 3 points, find the interpolating parabola that passes through them, and then the minimum of that interpolating quadratic is our next approximation to the actual minimum of the function. Finally, we looked at Brent's method. Brent's method is a minimization method that parallels the Brent-Dekker method for finding a root. It uses either the golden ratio search or successive parabolic interpolation while guaranteeing that the minimum is bracketed, and consequently tries to use the second technique where possible, unless it can show that the second technique is likely not working, in which case it falls back on the golden ratio search. Again, this is a technique that is a hybrid of two other techniques, one that is guaranteed to converge but slow, the other which usually works, but if it fails, it can fail catastrophically. So once again, we jump between these two as appropriate using Brent's method. Then we found the minima of a real valued function of a vector variable, and we looked at the following algorithms. The Hooke-Jeeves method did not assume we had a derivative and instead just explores and tries to find a direction in which the minimum is most likely to occur and then moves in that direction. Again, using only sampling. We then described Newton's method for finding extrema in n dimensions. And this involved creating the Hessian matrix and the gradient. However, if it's not reasonable to calculate the Hessian or not possible to calculate it, we can just use gradient descent. We can either calculate or even just estimate the gradient. The gradient gives the direction of maximum increase of the function, and so if we are finding a minimum, that means we'd like to go in the exact opposite direction. What we then described was how we can convert a n-dimensional problem into a one-dimensional problem. And once we have a one-dimensional problem, we can use all of the techniques we saw previously for finding a minimum along that one-dimensional line. Once we get that minimum, then we recalculate the gradient and carry on from that point forward. So we convert an n-dimensional problem into a one-dimensional problem. So this is a nice technique that transforms a difficult problem into an easier problem. Just like Newton's method in n dimensions converted a non-linear equation problem into a linear equation problem. So, following this course, you are now aware that there are issues when we represent real numbers as finite precision floating point numbers. You understand that there are tools that can be used to mitigate the issues that arise when using floating point numbers. And we have seen the application of these tools over and over again to approximate solutions in the following four classes of problems that have numerical solutions: evaluating an expression, approximating solutions to algebraic equations and systems thereof, approximating solutions to analytic equations and systems thereof, and optimization problems. I hope you had an enjoyable course. Good luck studying, and see you all at the examination. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!